Hey guys, I'm going to be going over chapter 5, atmospheric pressure and wind. Okay, let's get started. This is for your physical geography class. So today we're going to be going over nature of atmospheric pressure, density and pressure, those relationships, temperature and pressure. You guys can read through this. Okay. All right. So when it comes to pressure, I think this is the hardest to understand because our bodies can't really feel the small changes in the atmosphere. But it is very important to a lot of atmospheric processes. It's a very important feature of the atmosphere. It's tied closely to other weather elements, and understanding this concept in this chapter is going to be pretty important for the rest of the semester. So chapter 5, obviously, chapter 6, 7. So hopefully you guys are able to understand this. And again, given the climate of what's going on, this is not the same as being inside of classroom, but I'm going to do my best, okay? Hope you guys really listen to the entire lecture. Quickly, why do your ears pop? That's one way that we can really feel pressure and the pressure differences, right? So when you go in the airplane, or even to like a higher city or a city with higher elevation, you can feel that difference, right? So you have the pressure from down here, wherever it's at, like Whittier, California, and you're driving up to Big Bear, and then you feel a pop in your ear because between this little membrane in your head, you have the pressure from below, right? Like Whittier, California, and then it wants to expand because there's higher pressure closer to sea level. Okay, and so you really experience a popping. There's like a little membrane and it pops open. Okay, so that's just really quickly for you kind of to realize that even though we can't see pressure, it's something we do feel, right? Sometimes you go to the gym and people are like working out with that little mask on and they think they're super cool. I don't know what that's for. Maybe it's to show off, but I mean, they're trying to simulate that, they're working out at higher pressure or whatever the case is. So nature of atmospheric pressure. So what is pressure? If we were to look at the atmosphere, we know it has a weight, right? But that's hard to understand because we can't feel it. So think of the lobster at the bottom of the ocean. Can it feel the weight of the ocean on top of it? No, right? Can we feel the weight of the ocean of atmosphere on top of us? No, right? But the atmosphere does have a weight. So we're going to call that atmospheric pressure. Here is the definition for atmospheric pressure. It's a force exerted by the weight of gas molecules on a unit of area of the surface of Earth or any other surface or body, right? The higher up in altitude we go, the less pressure there is. So here close to sea level, Whittier, Fullerton, wherever you're at, there's going to be more atmosphere on top of you than as you go up in altitude, right? So like you go up to Big Bear, obviously there's less pressure, or there's less molecules of air, okay? So I want to show you this picture really quickly. Here, if you look closer to sea level, there's more atmospheric molecules. Obviously, we can't see that. We can't see the molecules of air in the atmosphere, right? But we know they're there. So there's more of those closer to the surface of Earth than as you go up in the atmosphere or in elevation, whatever the case, right? So two different things are going to influence pressure, okay? It's going to be density, obviously, number one. So what we're saying is that the closer you are to the atmosphere, right, down here, there's more of those little air molecules versus up here. Does that make sense? So lower altitudes, gas molecules are packed more densely, okay? And then higher altitudes, they're less dense, right? Okay, I'm kind of new to this, so let's see if this works. So, yeah. So say we're here, right? Cool. Close to the ocean, and then here's Big Bear, right? Or a mountain. There's more little molecules of air close to us here, right? Versus up here. So if you were to take a box of imaginary air, there's more molecules packed in there than there is up here. You guys got that? Okay. Oh, this is pretty cool. You just erase. All right, so let's go on to another influence on pressure. Okay? So temperature and pressure. So remember when we talked about how water boils, right? You put heat under that pot of water and those molecules start jiggling, right? Because it increases that energy and they start bumping into each other and then they get hotter. Think of that same idea. So say you have, let's use green. No, let's use purple. Say you have this, box of air here, correct? And then you have all these little molecules of air inside. Cool, 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 right? And then you're going to turn up the heat. Those gas molecules start to get agitated, right? And they bump into each other. They're bumping into each other. So this increases the temperature, okay? An increase in temperature of gas means that there's higher pressure. If you were to cool these down, they're not going to bump into each other, meaning there's a decrease in pressure. So if all other conditions stay the same. So increase in temperature, increase in pressure. Okay, got to remember that. Increase in temperature, increase in pressure, decrease in temperature, decrease in pressure. Ooh, that's my doggy. Calm down. All right, so these are dynamic influences. Remember, we're looking at the way air rises, okay? So we have molecules of gas here. They're warmed up. What happens when air warms? It rises, okay? As that air warms, there's more molecules up here, less here. Does that make sense? So up here would be higher pressure, and down here would be low pressure, okay? So strong descending air, you have high pressure at the surface, which means that as all these little molecules come down to the surface of Earth, they rush all the way down here. Down here, there's higher pressure. You guys like my little drawings? They're ridiculous, but hopefully you're understanding this. All right, so strong rising air, low pressure at the surface, because all that air has risen, there's less air at the surface. All right? Okay, let's keep going. So very cold surfaces are associated with high pressure. Warm surface conditions are associated with low pressure. Why? Well, think of the equator, right? The equator is mostly ocean. And the equator gets sunlight, probably the most out of any other latitude on Earth, right? What happens when you heat up water or the ocean? It evaporates, right? So when we have evaporation, that means that those molecules are jiggling and they rise up, right? They go all the way up, and what do they form? Clouds, okay, right? Evaporation and then condensation, right? This is the equator. Lots of sun going on here, right? This is a warm surface, and because that surface is water that warms, it evaporates, okay? Cold surfaces are associated with high pressure only because that air that is descending to the surface, it rushes outward, okay? So air is descending, the high pressure is at the surface. This is relatively colder. Doesn't mean it's like 30 degrees, it's just relatively colder. So we're going to call this surface low pressure, and that's how we're going to write it. This surface high pressure. Okay, so let's keep going. So how do you map them? So if you were to have high pressure, you map it in millibars. This is how it shows up on the map. Your relative conditions, pressure that is higher and lower than surrounding. This probably doesn't make sense to you quite yet, but I want you to look at, I'll get to the picture. So when we look at wind, because that's really what we're headed to in this chapter, we're looking at what makes wind move. Wind is the movement of air horizontally, right? But wind will move from high to low pressure. So if there's, say there's a lot of pressure here, right? A lot of air molecules. You guys see that? And there's less molecules here. Wind's going to move this way. High to low pressure. Keep that in your brain, okay? Wind moves from high to low pressure. This is on your quiz. This will show up again. This is what I want you guys to understand. And the fancy term for this, remember, because science is a bunch of fancy terms, is the pressure gradient, okay? So pressure gradient, wind moves from high pressure to low pressure. Pretty easy, right? That's it. So here's a picture, much better picture than the little crap drawings I've been showing you guys. This is obviously more air molecules on this side, so we're going to call it high pressure. Less molecules on this side, low pressure. Cool, right? It's what I was trying to draw for you guys. The direction of air will be from high to low pressure. Now, if we want to get on the scientific side of it, real sciencey, this would be considered 1020 millibars. That's how we measure pressure, okay? If you were in my lab, you would be definitely working with this. This would be 1018 millibars. Obviously, this is more than this, right? So if we were in a drone and we were looking over this picture here, it would look like this, right? High pressure here, low pressure here. Wind will always move from high to low pressure. Wind will always move from high to low pressure. So a few things are going to affect that movement of air, or the pressure gradient. Pressure gradient will always win. Wind will always move from high to low pressure. But you're going to have a couple things. Obviously, the Coriolis effect, right? The Earth is spinning. So we talked about that, I think, in chapter 3, and the deflection of air or water, right? The Earth is spinning. Say if we were like standing at the North Pole and I was throwing like an imaginary magical present down to New York, it wouldn't take that trajectory, right? It will conserve that momentum from the North Pole and it would deflect. So it would deflect. So you have to take that into account, okay? So winds will deflect. Yes, they're moving from high to low pressure, but because of the Coriolis effect, they're going to deflect, depending if you're in the northern or southern hemisphere. The friction layer will also affect the pressure gradient. Wind will always move from high to low pressure. However, closer to the surface of Earth at sea level, you have things going on that are going to reduce that. Okay, also the Coriolis effect is reduced closer to the surface. So yes, winds aloft, you have air moving from high to low pressure, of course. But closer to the surface of Earth, you have things like canyons, buildings, mountains. I mean, you name it. There's more friction, so air is more turbulent, okay? So pressure gradient, Coriolis effect, friction, all these things play a role when we're talking about wind movement, okay? How is wind measured? In knots. Persistent winds are usually in coastal areas or high mountain areas. Winds tend to move faster above the friction layer, winds aloft. Okay, so let's get to cyclones and anticyclones. When I say the word cyclone, what do you guys usually think about? Think about that movement, right? Maybe a tornado, a cyclonic movement. So it's just really the movement of air. And what we're looking at is either descending air at the surface, right? Or air that is rising. In both these cases, they're either converging winds here, converging at the surface and rising, or descending and diverging at the surface, okay? So this would be a high pressure surface because air is falling, right? Descending, there's more pressure here. And here, this would be a low pressure surface. That's how you would draw it, okay? These are distinct patterns around high and low pressure surfaces. All we're looking at is at the aerial view of this. The winds are moving outward, right? So this would be an anticyclone. This would be a cyclone. So we'll get to that in a little bit, okay? All right, so anticyclones, these are high pressure cells. Winds spiral outward from the center of cell. They diverge at the surface, okay? Descending, sinking air. Air comes down, descends, rushes down. There's high pressure at the surface. Winds are spiraling outwards. Because winds are coming down, it does not support precipitation because there's no airflow up here creating clouds. So it's going to give us clear skies, stable conditions, dry, fair weather. Not necessarily hot, but we tend to think hot when there's no clouds in the sky, right? And where we live here in Southern California, we're under a permanent ridge of high pressure, okay? So that's why we really always have sunny skies. So how would you draw this? If I were up here in a helicopter looking down and I could see all this imaginary stuff, it would look like this. You would do the H, high pressure. Yes. Winds spiral outward. And because of the Coriolis effect, right, they deflect this way. That's for the northern hemisphere. Got to take that click off, right? Sorry about that. Here is for the southern hemisphere. They spiral outwards, but they deflect the opposite way. This always confuses me. Yeah, you get it, right? This is southern hemisphere. Okay, I'll keep that there so you guys can look at that. Because this is when we use weather maps or whatever the case, this is how you would draw it. Obviously, it would look much nicer, but this is how you would draw it. Now, low pressure, so you have winds spiraling inward, right, and rising. Low pressure at the surface. So when air rises, what happens? It's evaporation, right? That water turns into a gas molecule and then it condenses at the top of the atmosphere, well, at the top of the troposphere. You have cloudy skies, wet, unstable weather. So if you were to watch the news currently, they'd be like, oh, today we have a ridge of low pressure coming in, some moisture. Yeah, because that's all the moisture in the air that's coming in, right? And if we have a ridge of high pressure in control, that means it's clear, stable weather. So how would you draw this? How would you correctly draw the cyclonic movement? So you drew an L, circle around it, right? Winds are converging, so they come in, right? Looks like this. There you go. All right. That's how it would be in the northern hemisphere. Southern hemisphere, they just deflect differently, but they're still coming in. Okay. Ta-da. Looks really shitty, and I apologize. All right, so let's keep going. So here's just what I drew, right? Anticyclonic diverging, cyclonic converging. Usually the western side of the United States has a ridge of high pressure in control. Eastern side usually has low pressure. Why? Think about these southern states, right? They're cloudy, they're muggy. Not always, obviously, these wax and wane, but think about that, okay? Here's that vertical movement. This is a much better picture than what I was attempting to draw, right? Air rises. As air rises, it condenses and forms those clouds. Remember, they're rushing inward, converging, and rising. These are descending and diverging. Okay? Again, here is that picture. You have high pressure, which is air diverging at the surface, and air moves from high to low pressure. Remember that? So the wind will always be moving towards that low pressure and then converging and rising. Okay, so this would probably be, maybe like the Great Basin over here, and over here is close to the Midwest. So when we look at these large maps, this is what they look like. Not all the time, but usually. Okay, so now we're going to go to a very important portion of this chapter. And if you look under your modules, there is a link for another professor going through what we're going to go through. Okay, so now globally, we're going to look at the atmospheric global circulation. This is how heat moves latitudinally. We know that the equator gets most energy from the sun, right? How does that move all the way to the poles and back down again, right? So this is the principal mechanism for longitudinal heat transfer, okay? Keep in mind, air moves from high to low pressure, and we have the Coriolis effect that's going to tell us how those winds deflect. And we also have that friction layer, which is not going to really play a part into this because these are less regional. These are global wind systems. And now my dog is snoring. All right, so if the Earth weren't rotating, we know that at the equator there's a band of low pressure. Why? Because it is a warmer surface, right? Why is that? Because the sun's always hitting the equator. So it's a warmer surface, air is always rising, there's low pressure at the surface. And then the poles are a colder surface, right? So you would call that a high pressure surface. Air moves from high to low pressure, it's going to rise, then fall back down again. Rise, cool. Earth is not rotating, very simple, right? However, the Earth does rotate, so this is a little more complex. Okay, first let's talk about a Hadley cell. So I want you guys to imagine well, actually it's easier to show you this picture. Okay, we have the equator, right? And you have a band, a constant band of low pressure. All that means is that along 0 degrees, there's always low pressure here. Because the equator is more ocean, remember I talked about this, when you warm up ocean, water evaporates and forms clouds. So there's also this constant band of clouds, and we call that the ITCZ, which is the Intertropical Convergence Zone. There is another slide on that, but remember ITCZ. It's the band of clouds along the equator, okay? So you have this band of low pressure along the equator. Air is always rising, right? So you have warm air, it rises to the upper portions of the troposphere and condenses. Now, as it rises and condenses, that air evaporates, it's no longer warm up here. Up here now it's cold. And so what do we know about cold air? Cold air is heavy, right? Cold air is dense. It's not going to sink back down. It's going to, because the Earth is rotating, it's going to sink. It's either going to sink at 30 degrees north or 30 degrees south. Now, when it comes down here, now because that air is sinking at these 30 degrees, we would call that a high pressure zone because this air is coming down and sinking. Does that make sense? So as it sinks, now these trade winds push it back to 0 degrees. Rises, condenses, heavy, heavy cold air. It's not going to sink back down to 0. It's going to sink here, and then it keeps doing that. We call this a Hadley cell. I don't know if you guys can go back and watch this YouTube video. It's just the animation of what's going on here. Let's do this view here. Let's do this view. Yeah, so we're at 0 degrees. Air always rises, condenses, falls down at 30 degrees north, and this would be a high pressure. This would be low pressure, right? Trade winds move it up and comes down again. So, you know, technically right now, I would have you guys fill in the global circulation system, but I want you guys to do that with that YouTube link that I uploaded on modules, and go ahead and go through it yourself. And you know, draw it on a piece of paper, draw a big Earth, 0, 60, 90, 30, 60, 90, all the way up, okay? So a couple things, the Intertropical Convergence Zone, the ITCZ, you have the northeast and southeast trade winds coming together in this area of the equator. You have the subtropical highs. As those winds descend on 30 degrees north and 30 degrees south, that's what forms these subtropical highs. Okay, so 30 degrees north, 30 degrees south. And these are so permanent that they've been named the Hawaiian high, the Azores high. And if you look at the continents close to these highs, they're same type of climate. So you have very dry climate here. It's actually chaparral. We'll get into that in chapter 8. Dry climate here, dry, not dry, but like semi-dry. So you have dry summers, mild, wet winters, right? That's what Southern California is like. And guess what? That's what Chile is like too, and South Africa, and Southwest Australia, and the Mediterranean basin. This is all Mediterranean climate zone because of these permanent high pressure zones. It's not like a coincidence. Winds are named in the direction they're coming from. So if they're westerlies, they come from the west. If they're easterlies, they come from the east. Okay. All right, so let's look at some regional wind patterns. You have monsoons where you have reversing tropical winds. However, it might sound like, oh my gosh, a lot of rain, but it's very necessary in India. They rely on the monsoon for their agriculture and other places as well, but just highlighting South Asia right now. So let's look at the general pattern. On a normal, you have your winter, right? Your winds are coming close to the equator, correct? The trade winds, they meet at the equator and then they rise and they form the ITCZ and they fall back down again, right? Well, what happens is this ITCZ meanders way up here. So instead of these winds meeting down here, they meet up here. So they bring in this warm ocean water onto land, which comes in rainfall, right? So your general pattern is here. Normal, everything's working fine, but then those trade winds reverse. So that's what's going on. The trade winds are reversing. And here is that ITCZ. Yes, it's at the equator, but it doesn't mean that it has to be at 0 degrees. Okay, so it meanders. It means that the cloud, that band of clouds, it rises and falls a little bit. So these winds, the trade winds here, kind of are thrown off. But, you know, they're used to this. It brings in that monsoonal moisture, also in East Asia too, all over here. So here's that intertropical convergence zone. If you bring up any picture of Earth, a satellite picture of Earth, you will always see a constant band of clouds along the equator. And that's the ITCZ. Always, always, always. And you also think about the equator, that's where we have most of our rainforests, right? So, I mean, it's not a coincidence. So lots of rain, lush green, broad-leafed trees and vegetation. So because they have that rainfall all year long, and you also have climates that are not like, they don't really get summer, spring, fall. They're really just universally rainy all the time because they're at the equator. All right, localized wind systems. So you have to remember, keep this in your mind, wind moves from high to, yeah, I could hear you guys almost in my mind, low pressure, right? So these are more localized. So this is something that we deal with here. Like if you were in Colorado or, I don't know, Nebraska, you probably would not be learning about these onshore flows, offshore flows, okay? This is very localized to us. So remember, wind moves from high to low pressure. So let's look at daytime. Okay, so it's daytime, all right? You're at the beach, land and sea. During the day, what heats up more rapidly? Is it land or water? Land, good. So it's a warmer surface. So this would be low pressure here, warm surface. This would be a cooler surface, right? So high pressure here. So wind moves from what to what? High to low pressure. So this would be an onshore flow, okay? That's why during the summer, where do you go? To the beach, right? Because it's nice and cool because you're getting all that natural AC. All right, let's do nighttime. It's nighttime. Got your land and sea here, right? What heats up and cools down more rapidly? Land. So land has cooled down already more, right? So the ocean is relatively warmer because it takes a lot of time to cool that down. So you have a high pressure over land, low pressure over water. Wind moves from what to what? High to low. So this would be an offshore flow. Guess what? I have a much better picture than these crappy second graders can probably draw better than that. So here, same thing. Land breeze, sea breeze. Daytime comes onto land. Oh, you're nice and cool, right? It's your natural AC. Nighttime, it comes off of land, okay? Regional wind systems. Now we get to learn about these Santa Ana winds. I know you guys have been wondering about them your whole life, right? They are an offshore flow. What does that mean? So they're going to be blowing offshore. They're warm, and why is that important? Because when we have the Santa Ana wind season, that's unfortunately usually high fire danger also, or high fire season or whatever, right? So those two things don't help, and that's usually when we have a lot of our brush fires. So the Santa Ana winds actually have nothing to do with the beautiful city of Santa Ana. No shade. They have nothing to do with Santa Ana. They start actually in the Great Basin. So think Utah, Nevada, Idaho, way up there, right? So during this season, you have a high pressure zone in the Great Basin and low pressure off the coast of Southern California. So these winds are moving from the Great Basin down to off the coast because they're an offshore flow off Southern California. As they go, they go down in elevation, so they're compressed. The winds are compressed. That's why they're warmer. And they're squeezed through this canyon. So they start up here, and they come down to this low pressure. So you have high pressure here, the low pressure here. So these winds are compressed. That's why they feel a little bit warmer. They pick up all the heat from the Mojave Desert as well. As they go down in elevation, they're squeezed, and they squeeze through the Santa Ana Canyon, which is closer to Diamond Bar and Chino Hills, actually. So it's not really Santa Ana Canyon in Santa Ana. It's just the name of that canyon, okay? So now you know. Now you can tell all your friends, hey, do you know what the Santa Ana winds are? Right? I know you guys are so excited about this. El Nino wind, El Nino Southern Oscillation, or ENSO. First, do you guys know why it's called El Nino? Well, a lot of this it really starts in the equatorial Pacific. That sounds fancy, right? But it's just in the equator, the Pacific Ocean, equatorial Pacific. Starts close to South America and during the month of December. So if you know anything about South America or Latin America in December, what are they waiting for? Who's the most important person? Not Santa Claus, it's baby Jesus. So that's why it's called El Nino. Aha, see, isn't that cool? So baby Jesus, that's really what it's about. El Nino Southern Oscillation, you have a reversal of winds. Normal days look like this. High pressure here, low pressure here. Trade winds are moving this way. Cool, everything works out cool. As those winds move, the water this way, cold water upwells. Here, cold water has more nutrients. More nutrients mean more fish. Peru has a huge fishing industry, so this is this is good, right? Fishing industry works well, everything's working normal. You have low pressure over here, lots of rain in the Philippines. Southeast Asia too. Like everything, this is the way it should be. Clear skies, cool. Now, the crazy thing is that atmospheric scientists don't really understand why this happens, but it is a reversal of trade winds. So instead of winds going this way, they now go this way. So now we have rainy conditions here, dry conditions here, no upwelling, no cold water, no nutrients, no fish for Peru. So that's just what happens in the equatorial Pacific. There are huge consequences all over the world. So we know here in Southern California there's a lot of rainfall, right? Peru loses its fishing industry. California sea lion populations also are affected because that cold water, it gives you more nutrients, right? Well, during an El Nino year is when your California sea lions are having their pups. And so our oceans get a tad bit warmer, which does not help in food sources for the California sea lions. So the moms will have their little babies and they go out and look for fish and they leave them and they don't come back because they can't find any because the El Nino has made the ocean temperatures warmer. So a lot of sea lions are left to starve. Floods in western and southern United States, tornadoes in southeast U.S., blizzards. There's issues all over the place, right? I think that's it. I think we finished, guys. Whoop, whoop. So I will also have this slide up without my voice, so you guys can click on these, all these links and watch the stuff yourself. All right, you guys, stay safe. I love y'all. Take care. We'll get through this. Bye.